Okay, good morning, good afternoon, good evening, everybody. Today we're going to be talking about experimental and theoretical probability in simulations and predictions. So there's a whole lot of unknown in that. There's 4 words that we need to understand what those mean in order to understand what this lesson is talking about. So experimental and theoretical probability are 2 different ways that we can look at the probability of things. So the names kind of give it away, which is really nice. So experimental probability is when we're actually doing an experiment. So it's the ratio of the number of times that an event occurs to the total number of trials. So if I actually do something, so if I were to look at, flipping a coin 10 times and saying, how many times did I land on heads? So this is what does actually happen. Theoretical probability is the probability of an event happening based on the possible outcome. So it's in theory. So it's what should happen. So if I go back to flipping a coin, if I think about it, out of 10 flips, in theory, I should get heads 50% of the time, right? Because my outcome is that I'm either going to get heads or tails, and they have equal probabilities. So in theory, I should get heads 50% of the time. But if I were to actually flip a coin 10 times, I might get heads 4 times, or I might get heads 7 times. So the experimental probability is what would actually happen, what does happen when I flip that coin. But in theory, what should happen. So again, the name kind of gives it away. So theoretical is what we think in theory should happen. Experimental is what we do in the experiment, what does happen. Now, sometimes we will use simulations in order to obtain the probability of various events. We can conduct a simulation. So it allows us to represent the likelihood of real life events occurring by using an experiment with similar probabilities. So this would be used when it's difficult to actually collect experimental data or when theoretical data might not be known. So what we could do for this is if I have, if I have a feeling that something is going to have like a 50-50 probability, that I could use tossing a coin to simulate that probability. Or if I think something has 1 in 6 probability of happening, I could roll a die and say, a 1 is like that event happening. And then when I roll the die, that's my simulation to see how many times do I actually get the 1. We're going to see a spinner shortly that I think will also help for you guys to understand simulations and how we can spin a spinner for simulations as well. So you're just going to have to bear with me on that one. And then we can use a random number generator. So what that does is it's a computer program that will generate a random number between a certain interval. So that would be nice if, again, I think something has like a 1 in 3, then I could generate numbers between 1, 2, and 3. Or if I think something has a 1 in 10, 1 in 10 chance of happening, I would generate numbers between 1 and 10 and see how many times 1 comes out. So those are a couple different ways that we can use things that we know the probability of it happening to simulate an actual event happening. The next thing we have is predictions. And this is really a big important concept in math and probability. That probability can be used to make predictions for future occurrences by setting up and solving a proportion. So one of the things I want to point out to you guys here, we've got some alliteration. Predictions, proportion, right? So when we hear of predicting data, we can set up and solve a proportion. Predictions, proportions. So this is when we know some probability and we want to predict based on the future or based on a larger scale. So for example, if we know that 50% of Mrs. Murphy's and Mrs. Rubin's students like Taco Tuesday lunch, then how many students in Todd Middle School would we expect to like Taco Tuesday lunch if there are 350 students at Todd Middle School? So I have information about that sample of Mrs. Murphy's and Mrs. Rubin's students that 50% of them like Taco Tuesday. So I want to predict something when this is where we have what would we expect to happen in our prediction based on the actual number of students at Todd Middle School. So what I can do is I could say that 50 out of 100 students, that's my 50% here, I would want to know then how many out of my 350 students. So this is where we're looking at setting up a proportion to predict something about those 350 students. So what I would do to solve this proportion, I can do my cross products here to say 100x is equal to 17,500. That's from the 50 times 350. And then I divide by 100 on both sides to get x equals 175 students. So my prediction would be based on that sample of students that my prediction is about 175 students would like Taco Tuesday. Now, predictions come with a little bit of wariness that it's not necessarily guaranteed that if I were to survey all 350 students, that 175 would like Taco Tuesday, but I'd expect to be close to that number. So maybe 160, maybe 180 students, but I'd be pretty close and pretty comfortable predicting around 175 students. So the next thing we're going to talk about is experimental and theoretical probability. And what I have for this is a really fun little spinner. So we're going to go to this website. And what this does for us is it helps us to understand the difference between theoretical, in theory, and experimental, what actually happens. So we see in this table that we have 4 colors set up, and we see our count, which is going to happen as we spin. And then we see our experimental percentage, and that's empty because we haven't done the experiment yet. And we see our theoretical percentage. So because this spinner has 4 equal sections, we would expect that 25% of the time, we're going to land on one of these colors, right? So 25% of the time, I will land on blue, or 25% of the time, I will land on red. So what's going to happen is as I actually spin this, so as I click the spin button and it goes through spinning, it will start to fill in the experimental probability. So the theoretical probability stays the same, and our experimental probability is based on what's coming out. So we're going to see as we keep spinning, it's going to keep changing that experimental data because it's based on what's actually happening, what does happen as I spin the spinner. So what's cool is the more that I spin the spinner, the more my experimental data should approach my theoretical data. So we might see sometimes that one color might come out a little bit more in the beginning, but the more times that I spin this, the more times that I go through my experiment, the better my data is going to be. So I'm going to spin this one at a time a couple of times more just to kind of give you guys an idea. So far yellow has not come out at all. And that's because in the real world, data is not always perfect. But that's not to say that yellow will never come out and that this, maybe isn't fair. It could be. Oh, there we go. We got yellow. So what's going to happen now is I'm going to run this experiment 100 times. And so I'm going to spin it, and then rather than watch it go through 100 times, I'm going to hit skip to end. So we see that our count has changed now because it's run through the 10 that we did manually and then another 100 spins through the simulation, right? This is simulating a spinner because I don't actually have a spinner to spin. But we're seeing that our data, this is really cool. So yellow had not come out at all in our first 10, or 1 out of 10 in our first 10, but now after 110 spins, it came out 30% of the time. It actually came out more than the other ones. So again, the more data collected, the better we're going to get. So now I'm going to change this to 1,000 spins. And I'm going to skip to the end because we don't want to watch that. And what we're seeing this, again, our experimental probability is really getting close to our theoretical probability. And as I were to keep going through this, we're going to keep seeing that experimental probability approaching our theoretical probability. Now, it might not ever actually get to exactly 25% of the time, so let's try it one more time. But we're going to get pretty close, right? So I can feel pretty comfortable with my experiment the more I do it, that the closer I'm going to get to that theoretical. So theoretical is, in theory, what we should expect to happen. Experimental is based on what actually happened when we spin the spinner. Okay. So we just kind of saw a simulation there already, but we can talk a little bit more about how simulations can be helpful. So we want to know what type of simulations could represent the same probability as the following situations. So we want something that's going to have the same probability that we could maybe manually go through and do it in a better way. So on a multiple choice question, there's a 25% chance of getting the answer correct. So to simulate if I were to guess on a multiple choice question, what's my probability of guessing the right answer? Well, it would be the same as that spinner we just did. So we could say spinning a spinner with 4 sections and getting, let's say, red if one section is red. Okay, so what I mean by that simulation is, so let's go back to our spinner here, and I'm going to reset this, okay? So this would be, we're going to say again, red would be like if I were to guess and get that question right. So let's say I had 10 multiple choice questions, and I want to know what's the probability, or like how would I pass if I were to just guess on those spins, right? So if I were to just guess on the question. So if I spin this and skip to the end, so this is saying that I would get about 30% because I'm getting 30% for the red. So if I were to guess on 10 questions, maybe I'd get 30% on that if I were to do it. So this has the same probability of getting red as it would be if I were to guess the right question or right answer on a multiple choice question. So we can use these simulations, which have similar probabilities, to determine the probability of a real situation without actually having to do it. All right, so number 2, we have the weather report shows that there is a 50% chance of rain. So this is very similar to if I were to flip a coin, because flipping a coin, I have a 50% chance of getting heads or a 50% chance of getting tails. So flipping a coin and landing on, let's say, tails being rain, right? So 50% chance of flipping my coin and landing on tails. So if I were to know, if it's going to rain, I can flip the coin. If it lands on tails, that'd be like saying, yes, it's going to rain tomorrow. All right, in our third example here, we can make predictions. And again, this is really the most important thing that we see with probability, is that we can get a sample of something and make a prediction about a bigger group. Okay, so Kinsey surveyed a random group of 7th graders as to whether they preferred video games, sports, or neither. Use the survey results to make predictions for the entire 7th grade class with 350 students. So she surveyed a small group of students, and we can actually add these up, 15 plus 22 plus 3, to get our total that she surveyed, 40 students. So we can take that 40 students that she surveyed, and we can hopefully make predictions about a bigger group. So in this case, the 7th graders, 350 students in the 7th grade. So I want to know, what is a reasonable prediction for the total number of 7th graders that prefer video games? So what I can do here is I can compare video games to our total number of students from the sample that she did, and then our actual situation. So again, predictions, we think predictions, proportions, right? So that alliteration. So video games, in our sample, it was 15 out of 40. And then in the real 350, we're going to say X number of students out of the 350 total. So we have our proportion. We're ready to do our cross products. So I multiply 40 times X, and then 15 times 350 to get 5,250. To solve for X, I'm going to divide both sides by 40, and I'm going to get X equals 131.25. Now, I've been a big advocate for units here, and this is where it's important. What are we talking about here? We're talking about students. Can I say 131.25 students? No, that's nonsense. You can't have 0.25 students. So we have to round it using our normal rounding rules here to 131 students. Now, again, we're just predicting. So if we were to actually survey the 350 students, it might not be that we're going to get exactly 131 that say, yes, they like video games, but we're going to be around that number, right? So again, maybe 125, maybe 140, something in that ballpark. All right, based on the information in this table, what is the most reasonable prediction for the number of votes for video games in the next 80 votes? All right, so based on the 40 students that we surveyed here, if we were to do another 80 students, how many would we expect to say video games? So again, we compare video games to total. So from my survey, we had 15 out of 40, and then we're going to look for how many out of the next 80. Now, here's a case where, yes, we could absolutely solve that proportion with cross products, or if you notice that this is increasing by a ratio of 2, by multiplying by 2, we can multiply both the top and bottom by 2, a good review of our proportions here, and we could say that it would be about 30 students. So if we were to survey another 80 students, we would expect about 30 of those 80 students would say, yes, they like video games. So predictions can be really helpful if we have a sample to look at another group that would have similar characteristics. All right, so we got 2 more examples here. Okay, number 1. So a board game has a spinner divided into equal sections of equal size. Each section is labeled with a number between 1 and 5. Now, some important things. They're telling us that the sections are equal size because that means that they have equal probability of occurring. So if I were to come back to that spinner for a moment, and if I were to look at my theoretical probability, here each of these are equal sections, so they have 25% of occurring. But if I were to change this so that maybe the blue was a bigger section, I'm going to see that that has a higher chance of occurring, and the yellow now has a smaller chance of occurring. So we have to be told that they're equal sections so that we know that the probability of those occurring would be the same. So that's why they're throwing that extra piece of information in, because that would change our probability. Okay. So we want to know which number in our answer choices is a reasonable estimate. And that's really looking at us predicting some future occurrence. So predictions, proportions. So what's a reasonable estimate of the number of times the spinner will land on a section labeled 5 over the course of 150 spins? So we're predicting in 150 spins, how many times would we expect to land on 5? So let's look at our actual spinner. We have 1, 2, 3 sections that are 5. So the probability of a 5 would be those 3 sections out of how many total sections? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 sections. So the probability of us landing on a 5 is 3 in 12. Now you could leave that as 3 over 12 for this proportion, excuse me, or you could simplify that down to 1/4. Either one is fine. We're going to use it to solve our proportion for that prediction of 150 spins. So we have our sample or our expected probability to be 3 out of 12. And then we're going to say how many times would we expect to get a 5 out of the next 150 spins. So we've set up our proportion. Now I'm ready to do my cross product here. So I'm going to multiply 12 times x, giving us 12x, and 3 times 150 is giving us 450. Solving for x, we're going to divide through by 12, and we're going to get x equals 37.5. Now I'm super excited because I've solved my proportion, but then I look at my answer choices and none of those perfectly match the 37.5. So this is where we have to go back to the fact that it wants an estimate from us here. So about closely to how many spins would we expect? Well, the closest one to that estimate of 37.5 is going to be choice C, 40 times. So we would expect, based on the probability of it being, 1/4 or 3/12 of the time, that we would get in 150 spins, about 40 times we would land on a 5. All right, number 2. A spinner with 7 equal-sized sections was used to play a game. It was used 250 times in the first game, and of those 250, the arrow landed on section 7 a total of 37 times. The same spinner was used 150 times in the second game. So I don't know how many times did the spinner most likely land on section 7 in the second game. So what we're going to do here is we're going to take information about the first game and we're going to use it to predict what the most likely outcome would be for the second game. So we're going to predict the second game. So let's look at our probability for the first game. So the probability of section 7 is going to be that we got 35 times out of 250 spins, right? So in 250 spins, we landed on section 7 35 times. So now I'm going to use this to predict, to set up a proportion to say that in the first game, we had 35 out of 250. So in the second game, I want to know how many out of the 150 would we expect to land on section 7, right? So if I only spin it 150 times the next time. So here we have our proportion. We can do our cross products. So we're going to get 250x equals 35 times 150. So that's 5,250. Dividing through by the 250 to solve, we're going to get x equals 21. Now this question's nice because that is actually an answer choice. So we would expect that about 21 times out of 150 spins. So some of the important concepts with probability here. We can use theoretical and experimental probability based on the situation. So if I know in theory what I should expect, then I can guess or estimate my probability in theory. If I don't, I might have to run an experiment. So in this case, they did the experiment of actually spinning the spinner to 250 times to see what the experimental data was, right? They actually spun the spinner 250 times. We can use both experimental and theoretical data with simulations and predictions. Simulations would be something like that spinner program that we were using, where we can go through it and see, what would we expect to happen based on some preconceived or understood percentage that we're expecting for our probability. And we can also use probability to make predictions, right? So here we just saw that case where they did the experiment to spin it 250 times, and then I'm going to use that probability to predict something about the next 150 spins in the second game. So all of these things really tie nicely together, but again, we have to understand what that vocab is talking about, and we have to understand how to solve these problems. So again, remember, predictions, proportions. All right, hope you guys enjoyed this probability video. See ya.